Okay, like I said last time, the last two sections in this chapter might seem a little bit bizarre. Or did I say that? In any case, the last two sections in this chapter might seem a little bit bizarre because we're going to talk about sequences. Limits sequences. But in order, what they will allow us to clarify certain parts of your current knowledge that are actually not as not as well founded as you might think. Okay. So sequences. Remember what a sequence is. What's a sequence? What's a sequence? Somebody tell me what a sequence is. Did anyone remember what a sequence is? Well, it's a function. It's a kind of function.
It's like a series of numbers that if you do something to the previous number, you get the next number.
Could be. So what you're describing is what's called a recursive sequence. So you have a number, and then it sort of do something to that number, you get another number. You do something to that, do the same thing to that number, get another number. That's what's called a recursive sequence. Sequence itself is just it's hard to describe it without using the word sequence. Right? You just said it's a series of numbers, right? But you could have just as well said it's a sequence of numbers. In any case, a sequence is a function, usually denoted by some small letter. Is a function on the natural numbers. Okay, so to every natural number, it gives you some answer, right? So it'll be like, right? So the graph of a sequence is something like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, blah, blah, right? It takes in a 1, right? It takes in a natural number and then returns some value, a at 1. Takes in a 2, returns some value. Takes in a 3, returns some value. Right? At each it's sometimes convenient to think of these as times, right? At time 1, it returns a value. At time 2, it gives you a value. At time 3, it gives you a value, etc., etc. And those times, for functions, you usually denote this with parentheses, but for sequences, one usually uses subscript. Okay. So taking n to a sub n. So a sub n denotes the nth term of the sequence. Right. So this function gives you a sequence of numbers. Right. It corresponds to just some sequence of numbers: a1, a2, a3, a4, etc. Okay. So for example, if I say a sub n is 1 minus 1 over 2 to the n, okay, this is a description of a sequence, right? So a1 is going to be 1 minus a half, a2 is going to be 1 minus a quarter, a3 is going to be 1 minus an eighth, etc., etc. You see how we describe sequences? Okay. Nothing too fancy. Okay. Can also describe them recursively. Remember the Fibonacci sequence where a1 was 1, a2 was 1, and then for n bigger than or equal to 3, an was defined as an minus 1 plus an minus 2. Right, the sum of the two preceding guys. Right, so a1 is 1, a2 is 1. A3, for a3 we'd say, oh, here's the rule, n is bigger than or equal to 3, so a3 is going to be a2 plus a1, so it's going to be 2. Right, a3, come up here. A3 is going to be A2 plus A1, right? Because it's going to be A3 is going to be A2 plus A1. So that's 2. A 4 is going to be a 3 plus a 2. That's 3. A 5 is going to be a 4 plus a 3. That's 5, and so on and so forth, right? That's a Fibonacci sequence. So this is another way of describing sequences, describing them as recursively. Okay, so just remember, these things are sequences, and this is how we describe them. Anyone confused at this point? I think we did this before. Okay. So we're going to do limits and sequences. And the same thing as limit of f of x as x goes to infinity being some number. This is very so limits of sequences. It's basically the same thing as what we were doing last time. The limit as x goes to infinity. Okay. So, right. Remember what the picture is there. Right. There's some L, and you have some function. And your function is getting closer and closer to L. Right. As x goes to infinity, your function is getting closer and closer to L. What did that mean? That meant that the formal definition was. Can anyone give me roughly what the what the mathematical definition of this was? I'll be impressed if you can. I won't be unimpressed if you cannot. Yeah, Kimaya. What does this mean mathematically? So sort of like the intuitive idea is you get closer and closer to L as x gets bigger and bigger, right? But that's not the mathematical definition. What's the mathematical definition? Go ahead, Kimaya.
The horizontal asymptote.
It's a horizontal asymptote. Okay, that's sort of like what we also call it. But Mariah, go ahead.
Isn't it like given an x, you can always find a place around L that's closer? Or no, wait, given a place, a tolerance around L,
Yes.
you can always find an x that's closer.
Almost. So given a place, very
Oh,
close.
no, you can always find a closer place around L.
Almost. Given an interval centered at L, given an interval centered at L, there is always not a place where you are in that interval, but there's always a. Okay.
Isn't there always a place where you're outside of that, like you're above that interval?
So yeah, you've got the right hands. You've got that right hand motion.
Okay, cool.
Not the right talking, but the right hand motion. Okay, so there's always a time past which everybody lies in that interval. Okay, so given any interval around L, there is a time n, so that in this, whenever you're past that time, f of x lies in your interval. Yeah, Mariah.
Wait, so can functions sometimes cross their asymptotes?
Yeah, that's okay.
Okay.
Yeah.
But
So
then isn't it technically like it? Okay, never mind.
yeah. So I know that in some, like, people often come in saying, no, functions aren't allowed to touch their asymptotes. It's just illegal. But it's okay. Yeah. For us, at least, I'm not sure why you want to do it that way, but we're not going to do it that way. Okay. So, given for the limit to be L means that given any interval, you can find a time, right? If I take a tiny interval around here, well, there's some time past which everybody lies in that tiny interval. Okay. No matter how tiny the interval you take around here, there's some time past which everybody lies in that tiny interval. Okay. So you do exactly the same thing for limits of sequences. So limit of sequence as n goes to infinity being L means exactly the same sort of thing, right? Here is your L saying, right? And then your sequence maybe is approaching L, right? Okay. For the limit to be L means exactly the same thing, right? Given any interval around L, whoops. Given any interval around L, there's a time n, so that if n is bigger than n, then a sub n lies in the tiny interval. Okay. So for example, let's come back to the example that we had before, 1 minus 2 to the n. Okay, right? So you look at the picture, right? Right, 1, 2, 3, 4, 5, etc. Right? At time 1, a 1 minus a half, time 2, a minus a quarter, time 3, 1 minus a fourth, 1 minus an eighth, 1 minus an eighth, minus a 16th, etc., etc. And the limit is what? What's the limit? 1, right? The limit is 1. Right? And let's see how that works, right? If I say, I'd like you to stay within, 0.1, I'd like you to stay within, a half of 1. Well, what's your n going to be?
3 or 1.
1? 3? Suppose I say, I'd like you to stay within a half of 1, right? Okay. Well, past what point does everybody lie within a half of 1? 1, or actually, maybe I should say 2, because you don't want to be on the edge of it. You want to actually be within a half, not equal to a half. Right? This is less than rather than less than or equal to. Yeah, Sarah.
Didn't you say just as long as it's greater than 1?
Yeah. So in fact, I could take n to be anything bigger than 2 or above. Right? 2 would work, 3 would work, 4 would work, 5 would work. Once I find a point that works, any number past that point is also going to work.
Okay, because it has to be a whole number.
Yeah,
Okay,
yeah.
I was
yeah.
wondering why it wasn't like 1.5.
Oh, I see. Yeah, one usually for sequences, one usually uses a whole number as the time.
Yeah.
Yeah, because the only things that you can put into it are whole numbers. Yeah. Yeah. I guess if this, yeah. Okay, right. And if I said I'd like you to stay within, a tenth of 1, what would you say? What would you take as your n?
Anything bigger than 4.
Anything bigger than 4, right? 4 or above, right? At 1/3, we're an eighth away from 1. At 1/4, we're 1/16 away from 1, and then after that, we're always closer than that. Okay, so anything 4 or above is going to work for epsilon being 0.1, 1/10, right? Right. And if I said I'd like you to stay within, here's the hard one. I'd like you to stay within epsilon of 1. I'd like you to stay within epsilon of 1. See if anyone can get it. I'll give a bonus point on the next exam to the first person who gets the answer. What should I take as my end? Kelly?
1 minus 1 over 1 minus epsilon.
1 minus 1 over 1 minus epsilon? Albert?
Maybe 1 or 2 to the end.
negative 1 over 2 to the n. Victor? Somebody gives you an epsilon and says, I'd like you to stay within an epsilon. Claire?
Is it 2 to the n times epsilon plus 1? And it's epsilon plus 1.
N times epsilon plus 1. I'm not sure if this will work. Sarah.
U1 minus 1 over epsilon.
1 minus 1 over epsilon. Some of these might actually work. Stefan.
Is there anything greater than
Okay. I'm not even sure if some of these work, but let me show you how. So you want everybody to be within epsilon of 1, right? Well, what's the difference between these guys? What's the difference between this guy and suppose we come out to the nth point. Okay. What's the difference between that guy and 1? Well, the difference is 1 over 2 to the n, right? And so we want that to be smaller than epsilon, right? We want that to be smaller than epsilon, and then after that, everything is good, right? So we want that to be smaller than epsilon. Well, what n do we choose? What n do you choose?
Oh, epsilon? N equals epsilon? Oh,
No.
infinity?
No. Infinity? No. We want an n. Okay, here's the question. You want an n so that this works. What? Maybe. So the hint is logarithm.
Yeah.
Logarithm. Oh, good, Mariah. Good.
Oh.
Good. I'm glad you said yeah. Right, yeah. Right. So you've got 2 to the minus n is less than epsilon. What kind of n? Solve for n basically. Right. What kind of n will make this happen? Let's take, say, natural log of both sides. Right. When you take the natural log, right, natural log of both sides. Right. The natural log is an increasing function, so when you take the natural log, you preserve the sign. Right. And then you say, well, negative n must be like this. You can pull remember property of a logarithm, you can pull the exponent out, right? And then let's, n has to be bigger than natural log of epsilon over natural log of 2 times the negative. That's negative 1. Right? So any n, just choose any n that is bigger than this. Choose any n that's bigger than that, and you're good. Okay, that was a hard one because you had to remember the natural log. But it wasn't hard if you remembered the natural log. So. Okay. Okay. But in any case, you see how to do it. Like somebody gives you an epsilon, and lo and behold, you can find some time past which that epsilon is satisfied. So the limit actually is 1. Yeah. No.
But like on this function,
Yeah.
it'll never go above 1, correct?
That's true. Yeah.
So would you still keep the L plus epsilon when you're talking about your interval and not?
You still keep that. That's still part of the definition.
Okay.
Yeah. Even though this is actually better than that, it actually stays within. It actually stays. We can actually find if n is bigger than n, L minus a sub n is less than epsilon. So we actually have something a little bit better.
Mm-hmm.
But we don't. We have something better. At least we have what we wanted, the definition of limit.
Okay.
Yeah. Yeah. So I mean, the only thing we need to do is lying between these two bars, right? And certainly we can do that. We can do better, even better than that. We lie between the lower bar and the limit itself. But in particular, we lie between these two bars. So. Okay, so so limits of sequences, basically the same thing as a limit of a function going to infinity, right? Same idea, right? Somebody gives you an epsilon, you can find a time past which that epsilon is satisfied. Okay. So you have the same sorts of theorems, right? If you have two sequences that are convergent. Okay. And being a convergent sequence means that they have limits. Okay. If you have two sequences like that, then basically all the theorems that you are used to will still hold, right? Limits and arithmetic work as you think they ought to, right? If you're taking the limit of a sum, it's going to be the sum of the limits. If you're taking the limit of a product, it's going to be the product of the limits. If you're taking the limit of a quotient, it's going to be the quotient of the limits as long as the lower guy is not zero, doesn't converge to zero, et cetera, et cetera. All those theorems that you had for functions still hold for limits of sequences. Okay. Also, we have a pinching theorem holds. We also have a uniqueness theorem, right? That there's only one number that could be the limit. If there is a limit, there's only one number. You good?
Yeah.
Okay. Okay. And fourth, and importantly, you have a limit, a theorem about limits in continuous functions. Okay. If the limit of a sub n is L as n goes to infinity, and n is continuous at L, then the limit of a sequence that you get by applying the function to each guy is going to be the function of the limit. Right? The limit of the function applied to the sequence is the function of the limit of the sequence. Right? You can pass the limit. You can pass the limit through the function if the function is continuous, just like we could for for limits of functions. So same sort of thing holds. For example, if I asked you what is the limit of sine of 1 over n as n goes to infinity. What's the limit of sine of 1 over n as n goes to infinity? Well, what's the limit of 1 over n as n goes to infinity? 0, right? And you'd say, well, the sine is continuous at 0, so I can pass the limit through. So this is going to be the sine of 0. Right? Because the sine is continuous, so I can pass the limit through and say it's the sine of the limit, which is 0. Okay. So limits of sequences and continuous functions interact just as in just as friendly a manner as they did in the previous for limits of functions. Yeah, Mariah.
Wait, sorry, what is the conversion sequence again?
Convergent means they have a finite limit. They just means they have a limit.
Okay.
Okay. So here, the sequence has a limit. If this happens, we say a sub n converges to L. We say this, the sequence converges to L. People often write, they abbreviate that with an arrow. A sub n goes to L. Okay. Okay. So some other things that I'm just gonna give to you. They're sort of obvious. They're what you might expect would happen. If p is some positive number, and we look at the limit of n to the p as n goes to infinity, what's going to happen? It's going to go to infinity. Right? You have p may be some small power, right? It could be like a square root, say. But you're taking the square root of n as n goes to infinity. Right? As n gets huge, this n to the p is going to get huge, even if the p is some tiny number. So just as you would expect. And sort of related, when I look at 1 over n to the p as n goes to infinity, well, that's going to be 0, right? Because n to the p goes to infinity, 1 over n to the p is going to go to 0. Let r just be some real number. What happens to r to the n as n goes to infinity? What happens to r to the n as n goes to infinity? What happens to r to the n as n goes to infinity? Right? R is some number. Yeah, Megan. Versus infinity? Maybe?
If r is greater than 1, it'll approach infinity.
If r is bigger than 1, it goes to infinity? What about if it's a negative number?
It's less than -1, it'll approach infinity as well.
If it's less than -1, what will happen to it? Okay.
Wouldn't it like oscillate because it'll be negative for negative powers and then positive for positive powers?
That's right. Because depending on the number, if the number is odd, then you have a negative number. If it's even, then you have a positive number. So it's a little bit, it's actually sort of harder to describe in that case, right? Okay, so this, so the moral is that it sort of depends, right? It sort of depends. So let me describe it like this. If the absolute value of r is smaller than 1, then the limit of r to the n as n goes to infinity is going to be 0. If the absolute value, if the size of the number is small, then the limit of r to the n is going to be 0. If the absolute value is bigger than 1, then the limit of the absolute value to the n is going to be infinity. Okay, so that it's about how, as good a description as any of how these things happen, right? If the absolute value is small, then you take greater and greater powers of it, it shrinks, right? The number starts shrinking. The size of the number keeps on shrinking and shrinks down to 0. Okay. Yeah, Victor.
What's the difference in part A between the limit going to infinity and the limit, or the it's just diverging?
This one? No, this one.
The other person.
Yeah. So this is the limit being infinite, which is that business of jumping over the bar. Do you remember? So as so let me spell it out here. The limit being infinity means that given, and so the picture is like this. Going up to infinity. What this is given any bar, there is a time past which everybody is above the bar. Do you remember how we described the limit being infinity for a function, right? Limit being infinity for a function was given any bar, there's an interval around here where everybody is above the bar, right? So here's something similar, right? Given any bar, there's a time past which everybody is above the bar. Okay, so stated more precisely, given any m, there exists a time so that if n is bigger than n, then a sub n exceeds the bar. So that's what that means precisely.
What's the magnitude?
There exists. Okay, and then there's one more sort of elementary fact, which is that the limit of p to the 1 over n as n goes to infinity actually is 1. If you take any positive number and you start taking higher and higher roots of it, then that number will tend to 1. You've probably seen this sort of thing playing with a calculator. You take some large number, you keep on taking square roots of it, and it heads down towards 1. Right? If you take some small number, you take square roots, more and more square roots of that, and it heads upwards towards 1. So I'm just going to give you these. I'm going to give you these facts, and we're going to use them to evaluate some limits. So let me give you some examples of evaluating limits. So, for example, the limit of n squared minus n over n squared plus n as n goes to infinity. Here's a sequence. Here's a sequence. Somebody asks you the limit of it as n goes to infinity. One thing you could do with this one is to just play the divide by highest power game, right? So we're going to divide top and bottom by n squared. Oops. Right. Divide top and bottom by n squared. The top turns into 1 minus 1 over n, the bottom turns into 1 plus 1 over n. Right? And then we use the property that the limit of a quotient is going to be the quotient of the limits as long as the denominator doesn't go to 0. Okay. So here we're dividing, multiplying by divide top and bottom by n squared. And here we see that this is 1 over 1 because the limit of a quotient is the quotient of the limits as long as the limit of the denominator is not 0. So I should say it's important to know why what you're doing is legal, right? Here it's okay to divide top and bottom by n squared because that's the same thing as multiplying by 1. You're always allowed to multiply by 1. Here, you're allowed to take the limit of the top and the limit of the bottom because of this quotient rule. Okay, so that's the important part. In addition to being able to evaluate the limits, you have to know, why what you're doing is justified. Okay. If I gave you this one, 2 to the minus j plus 3 as j goes to infinity, take a minute and see if you can do it. 2 to the minus j plus 3, 2 to the minus j plus 3 as j goes to infinity. Who can tell me about it? What's it going to be? It'll be 3? Because?
Because 2 to the negative j is the same thing as writing 1 over 2 to the j, which is j goes to infinity, that'll tend towards 0.
Right.
3 plus zeros.
Right. So by one of the facts over there, number A, letter A, this thing is going to go to 0. This thing is going to just stay at 3, right? And we know that the limit of a sum is the sum of the limits. So this is going to be the limit of 2 to the 1, 2 to the j, 2 to the minus j, plus the limit of 3. Right? The 3 is just 3. So you get 0 plus 3, which is 3. Another one. The limit of 2 plus cosine n over n squared as n goes to infinity. What are we going to use? Somebody tell me. Divide by the denominator. Sure. Okay, we could do that. So we get 2 over n squared plus cosine n over n squared over 1 as n goes to infinity. I just have to. I mean, that's you could say divide by the denominator, or you could say we're just separating the fraction. Okay. What happens? We know that this is if both the limits exist, and they will, then this is just the sum of the limits. Okay, what happens to the first limit?
It's 0.
It's 0. What happens to the second limit? Claire. What happens to the second limit? Or Sarah, go ahead.
Oh, it's also 0.
It's also 0 because of the.
Because of the it's a really high exponent. Or it'll go to like an infinitely large number, and then cosine stays at 1.
Okay, can you give me a theorem that will tell me that this goes to 0? Victor? Pinching theorem. Yeah, pinching theorem will do. Right, so you squeeze this thing between 1 and negative 1. 1 over n squared is going to go to 0. Negative 1 over n squared goes to 0. So this thing in the middle will go to 0. Right. Okay, so this is 0 by pinching theorem. This is 0 just by it. Okay. 2 more. This one is just a little tricky. It's not any more complicated than what you've done in the examples we've already shown. But it's just basically testing your understanding of the square root. Okay. Let me show you how to do it. You've got 4j on the top, you have the square root of j squared plus 5j plus 2 on the bottom. And basically, what you want to think, people are still counting. basically, the way you want to think about this is that, well, as the j goes to infinity, the 5j and the j squared basically dominates the 5j and the 2. Right? So this is basically going to be the square root of j squared. That, in other words, j. You've got 4j on the top and you've got j on the bottom, so this is going to go to 4.
Which one again?
Yes. Right. The j squared is going to be much bigger than the 5j and the 2, so we just ignore them. Okay. And so you've got the square root of j squared, in other words, j on the bottom. Right. So then you have 4j on the top, j on the bottom, so it's going to be 4.
Okay.
Okay. Now to do that more mathematically, to do that, spelling out exactly how it works, you could say I'm going to divide top and bottom by j. So I divide the top by j, and I divide the bottom by j. Okay. And then here's where you demonstrate your understanding of the square root function. Right. I'm going to move the 1 over j inside the square root. When I move it inside, it's the same thing as becoming 1 over j squared, right? Because if I pulled it out, it would be the square root of 1 over j squared. Right? So j squared plus 5j plus 2. This is something, from your pre-calculus knowledge, before calculus knowledge. Right? The 1 over j, I move it inside, it turns into 1 over j squared under the square root sign. Right? And so this turns into the limit as j goes to infinity of 4 over the square root of 1 plus 5 over j plus 2 over j squared. Okay. Now, we have this game of a bunch of quotients. We've got something over something, right? The limit of a quotient is going to be the quotient of the limits as long as the bottom doesn't tend to 0, right? So this is going to be 4 over the limit as j goes to infinity of the square root of 1 plus 5 over j plus 2 over j squared. Right? So this is, the rule here is the limit. The rule that we're using here is about the limit of a quotient, being the quotient of the limits. Okay. And at this point, what's going to happen? Looks like it's going to be 1. Why? Because we can pass the limit underneath the square root sign. Why can we do that? Because the square root is continuous. Right? So here we use the continuity. Right? Square root is continuous at 1. So this is going to be 4 over the square root of the limit of 1 plus 5 over j plus 2 over j squared, right? Which is 4 over the square root of 1. Let's just say 4. Okay. So again, the moral is, you are able to do these sorts of evaluations, but make sure that you know why you're able to do them. Okay. Because otherwise, you'll say, "Can I do that? Can I do that? I don't know. Can I do that?" Right? That's often the case. Is that, am I allowed to do that? Right. But if you know what's possible and what's not possible, then you can say, "Yeah, I can do that because this is continuous." Right? Yeah, Claire.
What are the numbers for in parentheses?
Those are actually problem numbers from the homework.
Oh, okay.
Yeah. Like what problem in the homework this came from. Yeah. Okay, so I hope to get to geometric series, a special type of sequence, today, but it looks like it's not going to happen. I actually do have your exams, if you want. Just stick around and get them. So just one comment on the grading. At the bottom of the front page, there'll be some number. It could be like this. That's not a number, it's letters. Okay, there'll be some letters at the bottom. Okay, it could be something like this. If it's this, it means that it's a low A. Right? It's an A bordering on an A minus. If it were the opposite direction, then it means it's an A minus bordering on an A. It's a very, very close to an A. Okay, that's just to give some finer gradation to the scale. Okay. Okay. And I'm returning them in alphabetical order. So